Welcome to the Institute of Biostatistics. I am Kadiru Jayaraman. The Institute of Biostatistics, BIOS for short, is an academic institution interested in collaborative works with other research organizations. Our details are available at inbis.com. The Institute has decided to initiate a series of lectures in applied statistics for the benefit of the researchers, slightly at an advanced level. And today, we are going to discuss about Bayesian analysis, which is the first lecture of this series. In statistics, there are two major lines of thought, namely frequentist and Bayesian, which differ with respect to their philosophy and methodology. Frequentist approach is largely due to R.A. Fisher, and Bayesian is accredited to Thomas Bayes. Ever since Bayesian came in, there have been heated debates between the two schools, but the Bayesians are having an upper hand in the recent times, as the approach has been found well suited for certain occasions where prior information can be utilized. In the present lecture, we will see what Bayesian approach has to offer and how it differs from the frequentist. The starting point of Bayesian approach has been Bayes' theorem. Bayes' theorem is concerned with conditional probability. To represent it mathematically, if X is the first event and B is the second event, then P B given X is our desired probability, which is obtained by the simplest expression of Bayes' theorem, that is P B given X equals Px given B into Pb divided by Px. The denominator can be expanded as Px given B into Pb plus Px given B dash into Pb dash, B dash indicating non-occurrence of the event. To take a real-life example, suppose that the results of breast cancer detection using mammograms come from the following situation. Based on the previous test, we know that, say, 1 out of 100 people have breast cancer at that particular time of the test in the population. Let B be the event of having breast cancer and B dash the event of not having breast cancer, and X the event of mammogram test positive. So this situation can be summarized in a two-way table. The overall incidence of cancer in the population, say, is 1%, and of not having cancer is 99%. Now, if a patient is having cancer, probability of the test getting positive is, say, 99%. And in the same case, test getting negative is 1%. If a patient is not having cancer, the test getting positive is, say, 1%, and test turning negative is 99%. So the corresponding the components are indicated in the table. Pxb given B, Px dash given B, and so on. So our interest now is in the conditional probability of cancer, given that the patient has been tested positive from mammogram results. So this can be obtained through Bayes' theorem, and we have the formula and all the components. On substitution, we are getting a value of 0.5, it is 50%. As per the above situation, the probability of having breast cancer, given the test is positive, is only 50%, which calls for a more sensitive diagnosis for a repetition of the test in such cases. The conditional probability of P given X is known as the posterior probability. So let us see what are the determinants of P of B given X. They are mostly the overall incidence of cancer in the population and the sensitivity of the test. So the above simple-looking Bayes theorem can be expanded or generalized, including that of the continuous variable. Here, the conditional probability of theta given y. Y represents the data or evidence. And the theta here represents some population about which we want to make the inference. So given data, what is the probability of theta assuming a certain value? That is the conditional probability here. This can be expressed by using Bayes' theorem as py given theta into pi theta divided by p of y. So which can be further expanded as the denominator as integral of py given theta into pi theta over the values of theta. The quantity py is called normalizing constant of the posterior distribution. It's also called marginal distribution and is often ignored as long as it is finite. Hence, we can write the above equation as p theta given y proportional to py given theta into pi theta, which is the py given theta is nothing but the likelihood, and pi of theta is we call prior information or prior distribution we assume for theta. And when multiplied, it results in the posterior distribution of theta given the data or y. As an example, consider a study of 14 students chosen at random, say produces 2 students with vision issues. The likelihood of this situation is obtained from the binomial distribution using the binomial formula NCR P raised to R Q raised to n minus R. Now, suppose for a set of given values, we assign prior weights, that is our belief about the possible values of P in advance. So here we center our population around the p-value of 0.15, and these are the successive probabilities we think it could be this situation. But this likelihood can be obtained as using binomial distribution formula. And now we multiply each of these values and prior into likelihood, and that is the value. When we add up, we get the normalizing constant. And in order to make this a proper distribution, we divide each of these values by the normalizing constant so that the sum is equal to 1. And this is called the posterior probability of P assuming each of these values. But essentially, Bayesian approach updates your beliefs about the parameters by accounting for additional data. This is our belief, this is the actual data, and the prior probabilities are getting updated using the actual data. That's what Bayesian approach does. Now, most often, closed-form solutions for the posterior distribution are not available, and we have to use simulation-based methods to estimate the posterior distribution itself. These methods involve repeatedly drawing samples from a target distribution and using the resulting samples to empirically approximate the posterior distribution. Markov chain Monte Carlo methods are used extensively for this purpose. In MCMC, samples are drawn from the probability distribution by constructing a Markov chain, where the next sample that is drawn from the probability distribution is dependent upon the last sample that was drawn. This is the Markovian property. The idea is that the chain will settle on the desired quantity we are inferring. The most common MCMC method is called Gibbs sampling, and a general version of this sampler is called Metropolis-Hastings algorithm. So what is Metropolis-Hastings algorithm? Briefly, the steps are as follows. We are at point X, say in the range of posterior distribution values. We make a guess for the next step. We will call this X star. We then compute the ratio of the probability of X star over X using the posterior distribution function. And if the ratio of px star to px, also called acceptance probability, is greater than 1, we accept x star as a new position. Even if the acceptance probability is less than 1, we don't automatically reject x star. We flip a coin by selecting a random number from a uniform distribution 0, 1. And if the number is smaller than the acceptance probability, we accept x star. If it is higher, we reject x star and start the process over again. So this way we can generate a series of values from the posterior distribution. In order to avoid the dependence of successive values, we can form subsets by selecting values at a constant interval, like in systematic sampling. We may have to discard a certain number of initial values to get to a stable or equilibrium stage for the distribution. Once we know the nature of the posterior distribution, we can work out the mean, confidence interval, and significance level for any value from the posterior distribution. In Bayesian analysis, parameters are random quantities that have distributions, as opposed to the fixed model parameters of classical statistics. The confidence intervals on the parameters are known as credible intervals, in contrast to fiducial intervals in the frequentist approach. There are two types of credible intervals. The equal credible interval describes the region between the cut points of the equal tail that has 100 into 1 minus alpha percentage mass, while the highest posterior density, HPD, is a region where the posterior probability of the region is 100 into 1 minus alpha percentage, and the minimum density at any point in that region is equal to or larger than the density any point outside that region. Now, something about prior distributions. Some of the distributions, like uniform distribution, are called non-informative priors, as they do not influence the posterior distribution. Jeffreys prior, proposed by Jeffreys in 1961, is a useful prior because it doesn't change much over the region in which the likelihood is significant and doesn't have large values outside that range. It's called a local uniformity property. Because it is locally uniform, it is a non-informative prior. Thus, it provides an automated way of finding a non-informative prior for any parametric model. It's also invariant with respect to one-to-one transformation. For instance, Jeffreys prior for binomial distribution is a beta distribution. This leads to a posterior distribution as a beta distribution, which is defined by this function. So one of the difficulties in Bayesian approach was to find an appropriate prior, and the non-informative, in the absence of any other information, we could choose or go for a non-informative prior. So now this is how Jeffreys prior works on the likelihood. So this thick solid line represents the likelihood function, and this U-shaped curve represents the Jeffreys prior, which is a beta distribution, and on multiplication, the resulting dotted curve is a posterior distribution. So for Jeffreys prior, we can see that the curve is almost flat within high density area of the likelihood. So thus it qualifies for a non-informative prior to a certain extent. A prior is a conjugate prior for a family of distributions if the prior and posterior distributions are from the same family. For instance, beta is a conjugate prior for the binomial distribution. Meaning, see this beta, if we choose it as a prior distribution and binomial likelihood, the posterior will all turn out to be beta. And similarly, for several other distributions like Bernoulli, negative binomial, geometric, beta acts as a conjugate prior. For continuous distributions, gamma can be chosen as a conjugate prior for binomial Poisson, normal, log normal, or exponential distribution, resulting in, again, a posterior distribution of gamma. So, now, conjugate priors result in closed form solutions for the posterior distribution, enabling either direct inference or classification of construction of efficient Markov chain Monte Carlo sampling algorithms. So, choice of conjugate prior results in simplification of the Bayesian methodology. I have an illustration of the Bayesian analysis through R, but I'm postponing that for the time being, just for want of time. What is the takeaway from this presentation? We have seen that Bayes' theorem paved the way for Bayesian mode of statistical analysis. Bayes' approach utilizes prior information about parameters to arrive at a posterior distribution from the prior and the likelihood of those observations. Further, all inferences are drawn from the posterior distribution. For posterior distribution that have no closed form solutions, MCMC is used to generate simulated data. Metropolis-Hastings algorithm is an important method in that regard. Unlike the frequent approach, Bayesian methods take the parameters as random and distributions of their own, with the distributions of their own. Ability to utilize accumulating data is an important feature of Bayesian approach. Unlike in frequentist approach, probability is interpreted as degree of belief in Bayesian methodology. Presently, the Bayesian methods are available for most of the common statistical routines like ANOVA, regression, tests of hypothesis, and so on. Several modules are available in SAS, Python, R, and other software packages to implement Bayesian techniques. And that's it. Thank you. And I shall put the illustration of Bayesian procedures using R as an annexure to this lecture. Thank you very much.